Hi everyone, welcome to the John Brooks company webinar on positive displacement pumps. My name is Stefan Fediw and I'm a technical sales rep for John Brooks. And joining me today is Chris Chapman. How are you doing, Chris? Maybe he's not there, I'm not sure.
I was on mute, I apologize.
Okay, you're on mute.
Okay,
I'm glad I asked then. Chris is also a technical sales rep with John Brooks company. And joining us in the background will be Paul Darcy, Director of Marketing. This webinar today is going to take about 45 minutes, and then that should leave enough time for some questions. But please feel free to fill in any questions you have in the Q&A section at the bottom of the screen. And we'll try and get to them as we go, but we may have to leave them till the end. Okay, so let's get started. Chris, do you like the graphics, first of all? Yes?
They are very fancy. They're getting fancier and fancier as these webinars progress.
Let's just hope the quality of the substance is getting better. We'll see. Okay, so John Brooks Company. We were established in 1938. We're a privately held Canadian company, proudly, and we have over 200 of us across Canada. So if we are a full-service national supplier of pumps, filtration, spray nozzles, custom skid packages, specialized valves, and pressure vessels. And today we're going to give away a couple of these e-gift cards again. That was quite popular last time, so we'll do that again. And we're going to go through today several different ways of conveying fluid in a positive displacement way. And we're going to start off with the air-operated diaphragm pump, a mechanical hydraulic actuated diaphragm pump, hydraulic actuated multiple diaphragm pump, internal rotary gear, external rotary gear, progressive cavity, peristaltic or hose pump, and then we'll just talk about a few packages that we could use in certain situations. So today we're going to be talking about positive displacement pumps. So if you remember a couple of webinars ago, we were talking about friction losses. Well, that still plays a role here. We're not going to get into it so much today, but essentially we'd probably be using Darcy Weisbach to calculate those friction losses as opposed to something that's more geared towards water like a Hazen and Williams. And again, just to kind of give you an idea of viscosities, on the left-hand side at the bottom of the screen, you see a liquid that's at about 100 SSU. And on the right-hand side, we have a liquid of about a quarter of a million SSU. Now, water at room temperature is about 30, 31 SSU. So I'm going to drop a ball through these liquids, and you're going to get a feeling of what these viscosities give you as far as a visual on their viscosity, these viscosity values. So you can see on the right-hand side, a quarter of a million SSU is kind of like cold honey. So just keep that in your mind, you know, when we're talking about viscosities. So there's really only two technologies out there to move fluid, and that's positive displacement pumps and centrifugal pumps. And we've spent some time over the last few webinars to talk about centrifugal pumps. Well, we're just going to review it quickly here again today because it is important. They are the lion's share of pumps out there. So a centrifugal pump, how does it work? Well, an impeller spins, and if we put fluid around that impeller, it will throw the liquid outward. That's a good thing because what's left behind is a void or a partial vacuum. And all pumps, whether positive displacement or centrifugal, always need some kind of low pressure zone at the suction side of that pump. So if we take this pump and let's say put it on a lift again, it's usually the best case to illustrate the vacuum being drawn. And in that container that we're trying to lift from, we're trying to pump from a well or a pond, there's atmospheric pressure pushing down on the top of that surface. And in the eye of the impeller, we've got a low pressure, which is something less than the outside pressure. So what we're going to do is we're going to set up a delta P or a differential, and we're going to push the fluid into the pump. I think I've said it a few times, Chris. You probably heard me say this a few times, and you probably will again. We do not suck. Pumps don't suck. We cannot pull on fluid. Fluid always has to be pushed. Fluid has no tensile strength, so fluid always has to be pushed into the pump. Why use positive displacement pumps? In general, a positive displacement pump is usually more expensive than a centrifugal pump for the same flows and heads. So there better be some really good reasons why we're using positive displacement pumps. The first is a viscous liquid. So let's take a look at a centrifugal pump, and we're going to get it going. And what we're going to do is we're going to spill some cold honey. And again, this is probably at that quarter million SSU or thereabouts. This cold honey trying to be pumped by the centrifugal pump is not going to be too successful. There's going to be a lot of shearing action. There's going to be a lot of horsepower consumed to try and move this fluid. Again, a centrifugal pump uses a lot of shearing, a lot of chopping action to move the fluid. It'd be kind of like going to your kitchen right now and pouring cold honey into your blender and turning it on. there's going to be a lot of horsepower consumed. So in that case, we would want to use a positive displacement pump with liquids that are higher in viscosity. Along the same idea, polymers. If we have a polymer, we get a pump going, we have a polymer, we pour out this polymer into the centrifugal pump. Well, you've paid some good money for that polymer. There's a reason why you're using this polymer. And putting it into a blender like a centrifugal pump, you're going to destroy that polymer or partially destroy it. So again, a positive displacement pump is usually more gentle, less shear. That's another reason to use it. And finally, constant flow rate. Maybe. It's a big question. Let's look at a flow head plot here. And if we have a system curve, again, what a system curve is friction and static, and it's the total resistance in the system. And all pumps that need to pump through that system need to obey the head flow relationship of that system curve. So if we put a centrifugal, an average centrifugal over this curve, where the system curve and the pump curve cross is where the pump will operate, both in flow and head. Well, here's what a 100% volumetrically efficient positive displacement pump curve should look like. It's not really a curve, it's a straight line. And what that's telling me is no matter what the head is, this pump will always deliver the same flow rate. So let's say this system curve changes. It becomes more resistive. Add some static, let's say. Well, the centrifugal pump is going to now start working back on its curve. It's going to start delivering less flow at higher pressures. Theoretically, a 100% operating volumetrically efficient positive displacement pump will just deliver the same flow at a higher head, okay? And that's a really important part of the metering and dosing world, the reason why we pay a little bit more for pumps that are positive displacement. We're going to talk about slip. That's going to be kind of the monkey in the works here. So positive displacement pumps and centrifugals. We've talked about centrifugals, let's talk about positive displacement. Positive displacement pumps use a change in volume to move a fluid. So we've got a gas here, let's say, and it's contained in a sealed container, and there's a certain pressure value in there. What happens if I reduce the volume, but keep the same number of molecules? Well, my pressure is going to go up. I'm squeezing this liquid or this gas, whatever it is. I'm squeezing it. Therefore, pressure is going to increase. Conversely, if I increase the volume, all these molecules spread out. They don't bounce into each other as much, and my pressure goes down. And this is the way a positive displacement pump generates vacuum or low pressure and high pressure on the discharge side. It changes volumes. Very simple. So here is an idealized reciprocating pump. Okay, so let's get it going here. As I lift the plunger upward, I am creating a volume in the cylinder. Therefore, pressure goes down, and my suction check valve, could be a ball or a flapper or whatever, opens up because there is some higher pressure liquid, atmospheric pressured liquid, or a tank or system pressure from the suction side that's driving this liquid into this low pressure volume. So that's our suction stroke. On the discharge stroke, we reduce the volume and therefore pressure increases. The suction check valve then checks, doesn't allow reverse flow, and the discharge check valve opens up and we get discharge flow. We'll just do that once again. Suction stroke, discharge stroke. Okay, reciprocating. And if we take a look at the displaced volume, is how much the volume changed. In this case, it would be the air volume of the cylinder from the lowest point of that plunger to the highest point of that plunger. And if we compare that to the pumped fluid, what went out the discharge, and we divide those two, we are going to get the volumetric efficiency of this pump. So best case scenario is if the pumped volume equals exactly the displaced volume, then this pump is 100% volumetrically efficient, or 1. Now, what happens if we pull a little dirty trick here? Let's take this plate out, this plunger plate, and let's drill a hole in it, okay? And then we're going to put it back, and we're going to take this back to its top stroke. Now, Chris, you got your microphone working?
I do.
Good. What will happen if on the downward stroke here, what's going to happen, do you think?
Someone's going to get sprayed in the face, so we're going to end up with liquid on the floor, possibly.
Okay, I agree. Do you think that discharge check valve will open?
It will, yes, I do.
And I think it will, depending on the size of the hole. So let's do that. We're going to push down, and we're going to, like you said, Chris, we're going to get this spraying upward because we've caused a high pressure and there's a way out. There's a lower pressure somewhere else. One in the discharge of the pump of the system, and then also one in free atmosphere. So this pump's volume now is decreased. Even though the pump itself dealt with probably the same amount of fluid, it actually moved the same amount of fluid, but the usable fluid that headed down that pipe, that discharge pipe, decreased. So therefore, the volumetric efficiency of this pump decreased. And the rest of it ended up on the floor. So all we have to do is to look for a pump with a big mess on the floor, and we've got a low volumetric efficient pump. That is true, but sometimes that is not always the way it works. Sometimes it doesn't appear on the floor. It slips back in other ways. So let's take a look at that. So let's bung that hole up with a tube, and let's send that tube back to both the discharge and the suction. Okay. Now, Chris, what do you think is going to happen as I push down? Let me get this started here. I'm going to push down, and we know that we're going to get this fluid going back up. Now, if you want to try and get this Tim Hortons gift card, you can here, Chris. But if anyone wants to type in and say either left or right, which way is this liquid going to go? Is it going to go this recirculating liquid right here that gets pressed out of the pump? Which way is it going to go, left or right?
We've got some answers. Well,
bit of a mixed bag.
No, actually, most people are saying right, but I'm not sure how many Timmy's cards we're giving away, but we do have some good answers here, and it's sending, and the answer's to the right.
Okay, and that makes sense, right? Where's the differential? Liquid goes from high pressure to low pressure. Well, it's going to go back to suction. It's not going to go back to discharge because it's pretty well the same pressure that's being generated inside that cylinder that's on the discharge side. So that's good. So the volumetric efficiency is still going to go down because some of that liquid went back to suction. We're going to have to pump that again. That's not what a pump is. A pump's not a mixer. We've got to get it out there. So the volumetric efficiency did go down. What's going to happen on my upstroke, Chris? As I come up with this stroke, what do you think is going to happen? Obviously, the suction check valve is going to open up. Does anyone have any ideas? As I open up the suction, where's the path of the flow going to happen? As I raise that piston, where's the flow path going to be? I'll answer it. It's going to go from the discharge side, which is somewhat pressurized, back to this low pressure zone, essentially. We know the discharge side is more pressurized than the suction side, and therefore it's going to go back to the cylinder. So we're going to get that reverse flow again, which is not good for volumetric efficiency. Again, we have to take that away. So if we have any kind of what we call slip, it's going to affect both suction stroke and discharge stroke. So just keep that in mind, or it may anyway. So volumetric efficiency, this is what it comes down to when you're looking at pumps, looking at applying pumps or using pumps. It comes down to really three main factors. This is what I see anyway. The delta P. What is the difference between the suction pressure and the discharge pressure when the pump is operating? The viscosity of the fluid, and also the pump technology. Because these two factors, viscosity and delta P, are going to affect different pumps in different ways. So let's go back here, do the same situation as we did before, and we're going to do a downward stroke, and we're going to get discharge flowing out, and we also know that we're going to get discharge back to the suction. But what's going to happen, so that's a certain amount of volume that's going to go back to the suction side. What's going to happen if we had a really high delta P? That means the discharge pressure was so much greater than the suction pressure. Do you think we're going to get even more recirculating back to suction? Yes, we will. So delta P in this situation is going to be that driver that drives that liquid from discharge back to suction and increase the slip. What do you think is going to happen with low viscosity? Chris, what do you think? If we're pumping something that is under high delta P and very thin, water-like, do you think that's going to increase this slip back to suction or decrease it?
I'd say it's going to increase it based on more thin flow through that smaller diameter pipe.
Less losses, right? It's a pump
Yes.
pumping down two parallel pipes. You're dead on. It's going to increase that flow back. So in some cases, we've got to be real careful when we start pumping low viscosity fluids against high delta Ps, because that liquid wants to get back somewhere and it'll find a path. And that's all going to affect volumetric efficiency. What if we do the same thing again, but this time against a low delta P? There's not much difference between the suction pressure and the discharge pressure. And we're pumping something very thick, highly viscous, really thick, cold honey. Do you think we're going to get a lot of slip back to suction, Chris?
No.
No, I don't think so either. This is the least situation where we're going to get the least amount of suck back to suction. But let's take a look at something else that's going on. Let's take a look at this discharge check valve. And let's take a look at the discharge check valve. And right now we are just finishing up our discharge stroke and we're getting flow from right to left, and that arm is opened up completely. What happens if we are now pumping some highly viscous fluids and we're just starting that suction stroke? So we're just about to start that suction stroke, and the flapper valve has not come down yet. It's going to try and come down, but it's going to have to shear through some really high viscous fluid, and it's going to be quite slow. And therefore, we're going to get a little bit of that liquid from the discharge side filling up the cylinder. That's not what we want. That's going to hurt us in volumetric efficiency. Let's do that again. This time, let's do it under a low viscosity fluid. That arm is going to seat very quickly because there's not a lot of viscosity that it has to travel through. There's less drag, okay? So that's low viscosity. So let's go back. Valves, whether ball or a flapper valve, high viscosity, low delta P, we have some slip taking place. That's the worst case for a check valve. High viscosity, low delta P. What's the worst thing for the pump itself? In this case anyway, low viscosity, high delta P. So I'm just trying to illustrate that there's no hard and fast rules. You really got to look at the application you're dealing with and know how to apply that pump correctly under the circumstances, and know about that pump, because this is just one single pump, a very simple reciprocating pump. You think that made sense, Chris?
I get it. But talking about how moving of different fluids, different viscosities of fluids at different pressures have an effect on pumps' internal or external slip.
Exactly. Good. Okay. So again, volumetric efficiency mainly depends on these three factors. Okay. And that's what we're going to kind of keep going back to. So, and also be careful, always be looking for these design holes when you're trying to apply a pump or when you try to troubleshoot a pump. Always be looking for these design holes. They may not smack you in the face this blatantly, but they are there. So Chris and I are going to keep going through this little page here and kind of discussing after we discuss each of the technologies, and just kind of have a quick discussion of, hey, this is good, this is bad. And it kind of maybe give you an idea on the pumps that you're applying now or trying to make work better in the future. So let's first of all work with the air operated double diaphragm pump, or AODD. Very common pump. Let's take a look at this cylinder here. It's got a shaft at the top. Let's take a look inside. And inside what we have is a plunger, okay? And that plunger is going to be actuated by the shaft that moves up and down. On the right side, we've got a suction check ball. And on the discharge, we've got a discharge check ball. And in the bottom, we've got this purple fluid that we're going to pump. So let's start this thing up. We're going to start with a downward stroke. And that downward stroke is going to be actuated by filling behind the diaphragm with compressed air. We're going to fill it behind. And what that's going to do on the right side, it's going to check that suction ball. So therefore, no liquid is going to be coming in or leaving that right side, but it's going to drive the discharge ball against maybe a perforated seat so flow can go around it. Then we're going to drive this even further down this, whoops, I'm going to hit the button, not the key. We're going to drive this even further down, increasing the pressure even more. So the stroke is going to finish right at this point, and we have discharged as much as we can out of this bowl. Then we're going to start the upstroke, and the upstroke is going to essentially be just something pulling on that shaft. And as we pull on that shaft, we're going to take away that compressed air that's entering, and we're going to exhaust the air that's behind that diaphragm. And we're going to continue to do that. And as we did that, we increased the volume of that purple area, unseating the suction ball, allowing flow to come in from the suction side. But we also seated the discharge check ball on the left-hand side. So we'll just do that a couple of times. And this is just one single way that this air-operated double diaphragm pump is going to operate, okay? Now, if we take one of those, and then we marry it to a second one, and they both share the same shaft in between, what we can do is we can now have this operate separately. When one side is on its discharge stroke, the other diaphragm is on its suction stroke, and vice versa. And as you can see, the suction and discharge locations vary as we get this backwards and forwards. Now, there is some switching mechanisms, some air valve mechanisms that's going to allow the exhausting and the pressurization of each chamber behind the diaphragm. And we'll just have a look at that in a quick video. But that's essentially the basics of a air-operated double diaphragm pump. And at the bottom here, these suctions will be tied together and manifolded, and the discharges will be manifolded, like you're about to see right here. So let's just start this little video here and show you now what it actually looks like. So again, you can see there's that shaft in between that's pushing and pulling each one of those diaphragms, and the air is actually what's doing the driving. That's actually closing those diaphragms in the discharge stroke. And we'll just let that run for a second. Chamber A, chamber B. So chamber A right now is being filled up with that compressed air, which is going to push against that diaphragm, which is going to squeeze the liquid out of the left side. And at the same time, it pulled along the diaphragm on the right side, causing its suction stroke, and therefore the suction ball lifting and filling. And then the opposite happens as the switcher changes, and how that switcher changes, very easy mechanism. We won't get into it today, but it's quite straightforward. And essentially, that's the way it works, an air-operated diaphragm pump. And this is what the curves look like. If we want to get 100 gallons a minute at about 60 psi, well, then we better drive this pump with about 90 psi of air pressure and a volume of about 80 cubic feet per minute. Okay, that's the way this works. It's not a positive displacement pump as far as vertical goes. It's got a lot of slip, I suppose would be the best term, and it sits more like a centrifugal pump curve. Okay, so it's a varying flow. So Chris, what do you think? Think its volumetric efficiency is pretty good?
It's going to be air based, is it not?
It is. So compressible, right? The air is compressible, so therefore we're not always getting that same amount of displacement every single time. It's going to vary on the back pressure, right? So we can't always guarantee the same amount of displacement and that motion of that diaphragm every single time. Delta P, well, it's going to depend on how much air we feed it to a certain amount, correct?
Yeah, being that it's very much like a centrifugal pump curve, if you go back, it actually has a shut-off value in essence. At zero flow, zero flow or deadhead, yeah. You can only generate so much pressure with a diaphragm pump, which is ultimately based on the pressure it's being fed from its system. Whereas we'll see further on that other PD pumps actually have potentially infinite pressures, potentially.
That's correct. And obviously pulsating flow, running dry. Yes, you can do that. Shear, not too bad. The balls will shear a little bit, do some shearing depending, but probably not the worst shearer in the world, not the best either, probably middle of the road somewhere. Okay, so let's now go into the mechanical / hydraulic actuated diaphragm pump. Well, it's a diaphragm pump, right, Chris? It's going to be the same. Well, let's see. It's got a motor, usually some kind of a linkage, mechanical linkage, maybe a gear or whatever else. And then here's the pump, single acting diaphragm pump. So let's take a look inside. What we have here is the reciprocating piston, which is going to go drive backwards and forwards. We're going to have an oil bath behind the diaphragm. And here's the diaphragm. And then here are the suction check balls and the discharge check ball. And finally, here's the pump fluid in pink. So let's get this thing going. Let's see what happens here. As we drive backwards, we are creating a volume. Therefore, pressure drops in the oil, and therefore low pressure on the one side of that diaphragm. Therefore, atmospheric pressure, tank pressure, system pressure is going to get drawn in or pushed in to is going to push the fluid into the suction side, unseat that ball onto the perforated seat, and we're going to get some internal suction flow. Then on the discharge stroke, we're going to squeeze that, compress that oil if we can. It's an oil after all. So that diaphragm is going to move forward and we're going to get our discharge stroke. We're going to pressurize that chamber and squeeze that liquid out the discharge. Let's do that a couple more times. So what's the main difference here then, Chris, do you think, from that air-operated diaphragm pump?
Yeah, the one that you've illustrated here is really hydraulically driven. So the AODD that we saw could be considered a mechanical because the diaphragm is connected to a rod. That rod is moving that diaphragm. Whereas here, what we've got is really something that acts like a piston pump in the fact that when that piston moves back, we create that vacuum, that low pressure in the oil. And as Steph says, the suction or the pressure, the higher pressure from the outside wants to get into that oil chamber. But the problem is there's a little diaphragm in the way. So therefore we end up having that diaphragm separating the fluid we're pumping from the oil that's generating basically the diaphragm movement. So it's a hydraulically driven diaphragm pump.
Exactly. So let's see how that affects things. Actually, first we'll show the video here. This is just a little thing that we set up at trade shows. And this is, I believe this is like a glycol surrounding a glycerin that's being pumped. And you can see this is a very pulsating flow. This is very pulsating. If you want a smooth flow, you're not going to go with this type of pump. But many times, hey, that's not a factor. So here, volumetric efficiency, very, very good volumetric efficiency. We could get some loss on those check balls if we get some really high viscosities. Delta P, very good. Viscosity, very good. Pulsating, hey, if that's a negative, then this is a bad pump for you. And low shear, again, we're going to be probably in that ball check kind of situation. Let's now go into something that's a little bit different. Maybe not a lot of people out there have seen this before. Hydraulically actuated multiple diaphragm pump. It's a bit of a different one. So here is, on the right side, we see a couple of, well, let me get it going. The black segment in the middle here that's flexing is the diaphragm. On the right side is the pumped liquid, and what you see on the bottom with that blue arrow is the suction check valve, and on the top is the discharge check valve. And as we actuate this piston on the left-hand side and the spring brings it back, we are moving oil towards this diaphragm, filling it up and pressurizing it. It's essentially the same thing as that single acting diaphragm pump that we just looked at. Single diaphragm pump that we just looked at. Essentially kind of the same idea. But in this case, and I'll just play this video, we have multiple of these diaphragms all acting at once. And this is a triplex one. We've got 3 diaphragms all acting at the same time, not at the same time, out of phase. And we'll see that this going right now as we get the valves back in, put the head back on. And inside we'll see all those diaphragms acting, but they're out of phase by 120 degrees. Because what we'll see later on is that there's a swash plate that's going to be activating them as it turns around. And there's the valve action as the liquid comes in and goes out. So let's just take a look at that here. So this is just one of those cells. And you can see that wobble plate behind. As it rotates, it's going to actuate all 3. There's going to be 3 of those cells. 2 you cannot see because it's not part of the cutaway. And as it actuates them, it's going to actuate them all out of phase by 120 degrees. So what does that give us? Well, let me get these started. 1, 2, 3. I've started those all out of phase. There are 3 diaphragm pumps right now acting in this video that you're seeing, all inside of one pump, but 3 individuals. Chris, that looks like pretty smooth flow. If I look at the very bottom of that quill, where that flow's exiting, that is some pretty smooth flow.
Yeah, we're getting, unfortunately, the video is a little bit jerky for me. Hopefully it isn't for everybody. But yeah, essentially, if you look really down at that tip, that nozzle there, you know, as Steph says, we're getting a smooth flow because when one diaphragm's in its discharge phase, the other one's probably halfway through a suction and the other one's through a complete suction. So we're getting a complete out of phase fluid movement.
So not all diaphragm pumps are high pulsating flows. And again, hey, as we pump against higher pressures, we're going to see a flow reduction at the same speed. That's something very common in many pumps for sure. And where we see this pump used a lot are in high washdown situations where, you know, there's a plant that has a large pump that's providing high pressure wash water. Well, that's okay when the pump's up, but when the plant's up and running and, you know, we need a ton of water at high pressures. But what happens when only one guy wants to run a couple of wands down in one corner of the plant? This big pump has to be running all the time, consuming energy. Well, here we have 1, 2, 3, 4, 5, about 6 pumps. And what they can do, they can be staged. So when there's a little bit of use, maybe 1 or 2 pumps come on. When there's big use, maybe 3, 4, 5, 6 pumps come on. So it's a little bit more energy efficient. You still get the high pressures that you need, but a little bit more flexible. And again, here, Chris, volumetric efficiency, good. Pressure, good. Viscosity, not bad, not bad. Pulsating flow, absolutely not. You know, mathematically it may be there, but if you take a look at the actual pulsations, no, it's very smooth. Low shear, well, you got those valves that are opening and closing again. That's going to add a bit of shear. Let's go to internal rotary gear pump. Very common design here. So this is a gear within a gear design. Essentially, we have one gear that rotates, or the outer gear rotates the inner gear together. And what we have is, let's say this is the suction side. These teeth are rotating within each other, and we are getting a opening or an unmeshing of these teeth right at this point. That means we're creating a volume. We're getting a volume that's increasing, therefore low pressure. And this liquid then goes around for a ride between these teeth and then gets squeezed out because we get another pressure change due to a change in volume. So let's take a look at a quick video of that right here. So on the right side, these teeth are opening up, unmeshing, creating a low pressure zone. Atmospheric pressure, tank pressure, system pressure pushes the fluid in. It fills those gaps. The liquid goes around for a ride. Nothing happens to it until it gets to the top and it gets squeezed out. Yes, we can run this in reverse. Just be careful of any pressure relief valves or check valves that you may have. So again, this is the setup that we have. Liquid comes in, goes out. And where do you think the slip's going to be? Well, from high pressure to low pressure, there could be some internal slip across the face of those gears. And if we take a look at how to prevent that, we have this head on the pump that if we can get this head nice and close like a wear plate, then maybe we can reduce some of that slippage. But let's say we've got some high pressure on the discharge side and some low pressure on the suction. So we've got a high delta P. This is one of our holes that we may have. Because if we have some low viscosity fluid that we're pumping against high pressure, we're going to be slipping back to suction quite readily. Whereas if we have some high viscosity fluid, we're not going to slip back so easily. It's going to be harder to get that liquid pushed through those smaller gaps, those recirculation gaps. And that's kind of shown here. Here we have speed and flow, and this would be for a high viscous liquid. If we now all of a sudden had some low viscosity liquid, this would all of a sudden drop right down. Pumping low viscosity fluid at, let's say, 400 psi that we could before with the high viscosity, we probably couldn't even achieve that now because it would be slipping back so much to the suction because it's so liquid, so water-like. So again, in this case, viscosity and delta P really drives the selection of this type of pump. Now, there are a few things you can do. Maybe there's a special setting that you could set here to reduce that gap if you know you're always going to be pumping some very thin fluids at high delta Ps. Again, there's always things you can try and do to reduce that slippage. So volumetric efficiency, pretty good on this pump. High delta P, can handle viscosities, very little pulsating flow, very little at all. There's so many teeth opening and closing, it's very hard to tell. Running dry, yes, you know, usually these are self-priming as well. If all they have to be is wetted in order to make the seal, and they can run dry. Just be careful of that mechanical seal. And then low shear, what do you think, Chris? Do you think this is a low shear pump?
It's pretty good, I would think.
Those teeth opening and closing, though, you know, we are getting some slicing, you know, there is that kind of thought there, but there's no valves.
It's check valveless, so you're not getting any balls opening and closing. So I think that, you know, you could look at either one.
Yeah, okay. Just for completeness, let's just look at that external rotary gear pump, kind of the brother of the one we just spoke about. Essentially here we have some teeth that are opening up, okay? As they open up, they create a low pressure zone. And that liquid then goes around the outside. I know a lot of people, hey, when I got into this business many years ago, I always wanted to say it goes through the middle. The liquid goes through the middle. Obviously, it cannot. There's no space for it to. It goes around the gears and then gets squeezed out as those gears mesh on the left-hand side. Again, the slip is going to probably be from discharge to suction across the end of that gear. And here's what it looks like essentially in 3D. Those gears are quite deep. And these are just spur gears in this case. And as you know, with anything, a gearbox or your car, spur gears are quite noisy and they usually have some speed limits. So if we ever do have to get into some high speeds, we'd probably go to a different type of gear, a helical or a herringbone gear, a high speed gear, which will work. Here, Chris, what do you think? Pretty well the same, I would say, as the internal rotary gear pump. Again, some shearing action, no pulsation really. Pretty well an all-round kind of positive displacement pump here. Nothing really hits the top of the list, but nothing hits the bottom of the list either, I would say.
No, I agree. Maybe not as much pressure as a internal gear pump, maybe.
I agree with that for sure. Yes, there's just the build of the internal rotary gear pump for sure.
Hey guys, it's Paul here. Just
yes.
wanted to comment on the dry running capability of any gear pump. Some of them can for a short period of time. I think long periods of time, longer than a half an hour. So you wouldn't really want to run a gear pump dry. You'll score the teeth, score the wear plates, and potentially increase the slippage.
Good point. Agreed. Yeah, what is dry running, right? To what extent are we talking about? A system upset for 2 or 3 minutes, probably okay. Yeah. But if you're talking about, you said like half an hour, yeah, I agree with you there, Paul.
Right.
Thanks. Okay, Chris, I think this is probably one of your favorite pumps, progressive cavity pump right here. You know, progressive cavity pump, I kind of think of it as a piston pump in series. It's a series of pockets that are going to get pushed along a long rotor. And I kind of think of it this way, because it's really hard to visualize what's going on inside a progressive cavity pump. And if you, let's play this video. If you can see, this pocket of fluid is getting pushed or progressively moving down the rotor and stator. So here, the rotor is the screw-like object in the middle that's rotating off balance, off center. And that's usually a hard metal, obviously. And the, whoops, let me go back here and play it again. And the stator is usually some kind of elastomeric, a little softer, a little more give to it. But there's always a seal, there's always a touch point here between that rotor and that stator. And that it can be a little bit of its Achilles heel. And here is really what we look at as far as a generic curve and kind of describes what's going on inside a progressive cavity pump. If we take a look at a flow rate, if we're pumping against low pressures, the powers are going to be quite low. We're not going to need too much power in order to pump against a low pressure. Makes sense. But our flow is going to be quite high. Now, if we have to start pumping against some higher pressures, our power is going to go up and our flow is going to drop off, again, due to that delta P. You know, we're going to get, that liquid isn't going to want to leave and go into that high pressure zone so easily. It's like that slip thought or concept. So again, higher pressures, usually a deterrent. on power, and many times a deterrent on the flow. And here is the actual video of the flow here. And Chris, that looks pretty smooth to me. There's a pretty well no pulsation here, right?
No, zero pulsation on a progressive cavity pump for sure.
And if you had to pick your shear favorite, the one that you had to use against a product that you did not want to shear at all, what would you use?
Yeah, definitely a progressive cavity. There's no check valves. I mean, everything we've looked at, well, apart from a gear pump, but the two diaphragm pumps we looked at had suction discharge check balls. Obviously, with the CPEXs, with the progressive cavity, there is no discharge or suction check valves to kind of give us any small gaps that might generate any kind of shearing action as we move fluid through them. So therefore, this progressive cavity is definitely the best for high sensitive or high shear products.
I think you've even seen it pump some chicken parts too, haven't you?
Yeah, it'll do some solids. It'll do, and they'll do some pretty nasty things if you put the right cutting devices in front of the pump.
Yeah. So not always clean fluids for positive displacement pumps. So I think we hit that point. No pulsation, low shear, volumetric efficiency, very good, and so you can get some high pressures as well.
High viscosities.
Not dry running. Yeah, I'll let you go for that one, Chris.
Sure, high. We can do some high viscosities given the right additional equipment to feed the suction. If it doesn't flow, then obviously it's not going to enter the pump. So we need some external devices like an Archimedes screw type system to get the fluid into the product into the pump to get it moving, because it won't flow in. But we can do some very high viscosities. But the big Achilles heel is cannot run dry. Steph mentioned that we've got some touch points between the rotor and the stator. If those touch points see any dry running or no lubricity, then they burn up pretty quick.
Yeah. Now there are some things we can put on there. We can put some temperature probes, right, Chris? If it heats up to a certain amount, it'll take the pump offline. But yeah. Okay. Finally, peristaltic or a hose pump. It's a different kind of pump. My good friend Al Moscosi out in Saskatoon, I hope he's listening today, he always describes this pump as taking a rolling pin to a garden hose. And I think that's great. He has some good insights. So if I were to take a pipe, steel pipe, stainless steel pipe, and I were to put a piston head in it, and I were to push that piston head along, what's going to happen is I'm going to pressurize the left-hand side because I'm decreasing the volume, and I'm kind of increasing the volume on the right side. I'm creating vacuum or less pressure. Same idea that happens with this peristaltic pump. So here we've got some kind of a rubbery elastomeric hose, hollow, and I'm going to put a roller, squeeze it down, and I've pretty well pinched off that roller. I've closed the inner diameter of that hose, and then I'm going to push it along, and on the back side I am creating this low pressure, this springing back effect. As we compress and then spring back that hose, it's creating a low pressure. I know we don't like that term, but it's creating that low pressure. It's creating that volume, and therefore that's our suction side. And obviously on the discharge side, rolling pin on a hose, we are pushing that liquid, we're squeezing that liquid through. And this is pretty well how it's made up here. We have the rotor with the two rollers, and then we have the hose, and then we have a discharge and a suction. These things can run backwards, just make sure of any valving in there. And we essentially have a very smooth, non-pulsating flow until it is pulsating. It stops immediately and then starts again. So it's a very long non-pulsation and then a pulsation. So again, this is a nice video to kind of show that. Very smooth, very laminar, but then boom, you're going to get that big drop. For higher pressures, we remove those rollers and we put shoes, and then we also get rid of that bar and beef it up a little bit by putting a cylinder in there so we can take those high pressures, and essentially it works the same way for high pressures. And again, this is a little bit different. Speed and flow are identical. As we increase speed, we should increase flow. And when we pump against some low pressure, we get a certain amount of power required. And as we pump against higher pressure, there's more power required. Heat does take into account here. Actually, heat with any of these diaphragm pumps or any elastomeric pump is going to affect the efficiency, the life. The heat will definitely affect this situation. And also, it's all about hose life. That hose is really the replaceable part. And if you can run it slowly, you're going to get more life. It cycles, 1 million cycles, 500,000 cycles, depending on the application. Once you reach that, you're pretty well done. And as you move out right on the right-hand side, you've got the intermittent service. You know, I think they say, you know, run for 1 hour, then stop for 2. You know, and then there's some real intermittent service, which is 1 hour a day. It's all about hose life, essentially. Lower the pressure, the abrasiveness of the liquid that you're pumping, maybe there's some acids or chemical attacks.
Large pump running slower to generate the same flow is going to give you much more life.
Good, yeah, large, and that's always a tough one. Larger, and that affects a lot of pumps. Large pump running slow. It's not because we want to sell a large pump. Well, it's nice to be able to sell a large pump as a salesperson, but it's going to give you the longevity, right? You're not going to wear it out as much, and that's where the factor comes into play. So here, volumetric efficiency, yeah, it's good. Delta P's to some extent. Viscosity, yes, very good in high viscosity. Extremely bad for pulsation. If you cannot handle a pulsating flow, this is not the pump. Chris, shear and dry running.
Both very good, yeah. You know, there's really no meshing components, so running dries, you know, fine. These things will self-prime very well as well. Low shear is good, and then the pressures again. You know, depending on the design, you have to make sure that you've got the right design or you pick the right pump to generate the pressures you need. But again, hose is dependent, rollers versus shoes. Another point on the pulsation is that you know, there's the potential to look at pumps that have, you know, more than 2 rollers or more than 2 shoes that perhaps reduce that pulsation.
That's a good point. Yes. Okay, thanks, Chris. And then finally, we got through this. Let's just take a look at one case where we would use a metering dosing pump, a very common application under pH control. So let's say we've got some waste leaving a facility, a plant, whatever. And at this moment in time, the waste is caustic. It's a base. What we would do, we'd have an analyzer, and we would start to inject some acid into that waste line in order to neutralize it. And that analyzer would constantly be analyzing the upstream, the downstream, and constantly adjusting how much flow is required of the acid or the base. We probably overshoot. That's the way life is. We have to get to the point by iteration. So at that point, we would either probably reduce the acid going in, the acid metering. We could put some OH in there too, some base. But you know, it would be the analyzer's choice and how this skid is set up, how we keep this outflow neutral. And this is quite crucial. Unfortunately, let me just go through the other case. We don't have a lot of time. So that's just when we have a acid base, we'll hit it with the caustic. Unfortunately, many times, just having a drum without any injection, just gravity injection, essentially, just won't overcome the pressures inside the pipe. So we have to add some pumps. And this is essentially the setup that we would have for the big metering side of things, as far as let's get the pH real close to neutral. And then we'd have a couple of pumps probably here to do what's called the polishing. Just trying to, you know, use a little bit of flow just to kind of get that right where we need it, instead of running these big pumps to, you know, to get that percentages of the pH just correct. Now, Chris, I know you have a bit of a problem with this. You're thinking these may not have been the right pumps, these single acting diaphragms for this application.
Yeah, I think it's worth pointing out that when we talked about the diaphragm pumps, we mentioned the pulsation was quite a big problem. And I kind of look at it in the fact that if you want to meter, if this was a bucket, you've got a pipe running along the bottom of the screen. But if you had a drum, or if you had a pit full of fluid, you might not care that you're getting a pulsating flow of your polishing fluids or your, you know, base and the acids into that tank, because you don't care how it's metered. But if you've got a moving liquid and you're pulsing, say, your acid into that moving fluid, that liquid's going to get dosed basically in chunks as opposed to a nice, smooth dosing action. And obviously then you can start looking at, okay, is the diaphragm pump the right right pump for the job, or is the diaphragm pump the right pump for the job based on many factors? But now we need to start looking at pulsation dampeners to put on the discharge side of this pump, so that when we enter the flow stream, we do have a nice laminar flow based on the fact that that pulsation dampener is taking up those high pulsations. But that's not always doable either, depending on chemicals, depending on the product that you're trying to pump. It may not be a nice acid or a nice base. So there's certain factors you have to consider. So not the wrong choice, but just something to factor in on how you want to meter, what it is you're metering, and what it is you're trying to meter with, to allow you to decide what kind of accessory equipment you can put on your system.
I think you're telling me that selecting pumps and pump systems, it's not something that you can just read up the night before on.
Pretty
You gotta kind of know, you gotta have some experience about it, right?
Got to take everything into account, as opposed to just how much flow and head. It's just not about flow and head, right?
It's not a pump in a box.
In a box, yeah.
So here's just some typical skids. I won't go through them. Many times we have to change the materials, plastics, PVC, stainless steel, wall mounted. There's all sorts out there, and obviously we do supply these. Just a few little things. We don't have a lot of time left. Just want to comment on relief valves. Please, positive displacement pumps, please put relief valves in them. If something happens and the discharge gets blocked or the suction gets blocked, mainly the discharge, something's going to give. Hopefully it's a motor or something and it gets tripped out.
I'm going to stop you there, Steph. I'm going to stop you there quickly, because we have a question that's worth answering based on that comment.
Okay.
So Nima said, how does deadhead of a PD pump be determined? So,
okay.
So the fact that you've just mentioned relief valves, I think, goes to the point of deadheading a positive displacement pump.
Yeah, and let's take aside that air-operated one. That's a special one. You deadhead that one, it just stalls, right?
But PD pumps, you never want to deadhead a PD pump.
Well, yeah, go on.
Go on. No, go on.
Well, that curve, the pump curve on a PD is vertical or close to it many times. That means they don't keep going vertical to infinity. Well, it won't. Something's going to break. It's not dying out. That pressure's not dying out like a centrifugal as we move over to the left-hand side to a finite number. It's going to keep going and going and going, because you're changing that volume. You're decreasing that volume on the discharge stroke. That means pressure's going up. And as long as you keep decreasing volume, pressure's going to go through the roof. There could be some slip points. There could be some internal slip that's going to take place. Pressure relief valve would be one of those. That would be a designed internal slip. There you go, Chris.
Yep. So hopefully that answered your question, Nima, about deadheading PD pumps.
Quick point in cavitation. Chris, can positive displacement pumps cavitate, do you think? Well, you know the answer to this.
Yes.
Okay, centrifugal pumps, there's three ways that they can cavitate: suction cavitation, recirculation cavitation, and discharge cavitation. With a positive displacement pump, the only way I see them cavitating is through suction cavitation. There could be the 1 in a million cases where the velocities are going so fast through a ball or a checkpoint that we could vaporize that fluid. Probably unlikely. Here, only suction cavitation. And let's take a look at this in our simple reciprocating case. We're going to go up for our suction stroke. And let's say there were so many restrictions on the suction side that there was so much friction that we drew a vacuum, and the vacuum was so great that we vaporized that fluid. And that's what we see at the top there, some big vapor bubbles. They probably won't be that big, but there's there. What's going to happen to those vapor bubbles now as we start that discharge stroke? They are going to collapse so fast that it's going to cause a hydraulic hammer, a bang. And this is going to happen every time we get that stroke, that discharge stroke. So if somebody says, I've got a noisy pump and I keep changing the check valves, and when I look at the check valves and the seats, they're all damaged. They're like they're being beaten up. It could be suction cavitation. Do you agree with that, Chris?
I do. Yes, a lot of damage and pitting on those balls potentially, and the seats.
Yeah. Okay. Just a quick reminder for next 2 weeks from today, June 11th, we will be talking about VFDs and applications, and we will be visiting the John Brooks Virtual Test Lab, and we'll put some pumps in this test lab, and we'll go through a few things that are going to be pretty cool, and maybe we can even take some questions and test some things that you want to know about as far as how pumps react to different situations. So that'll be on June 11th. variable frequency drives and pumps, centrifugal and positive displacement. Chris, I don't know if we've got a lot of time for questions.
Yeah, we are close. We only have a couple. I think one, there's an anonymous one that does that. If you want us to help you, you can let us know your contact information. But seem to have somebody that's having some trouble with an AOD, a diaphragm pump.
Okay.
If it says anonymous attendee, but if you want to let us know, we can get one of our guys to get in touch with you and help you troubleshoot that system. We can certainly do that. Is it possible to get a copy of this recording? So, Steph, do you want to mention things are on YouTube?
Yeah, yeah. What we're going to do now is we've changed things up a little bit. The next email that you get to say thank you for attending our webinar, you're going to get a link. And you press on that link and it's going to take you to our YouTube, I'm going to maybe use the wrong term, channel. And there will be every one of the webinars that we've done. And therefore, as it grows and we have more webinars, it'll just always be the same link that you go to. So that'll make it straightforward. So you'll receive that link for sure. Is that it, Chris, do you think?
Yep. I think we're good. We can. We'll follow up with a couple of other people here just because of the time that's gone on. But no, I think we're good.
Yeah, well, I think there are a few other questions. What we'll do is we'll have copies of them, and as you guys said, we're running out of time, so we'll address them by email and get back to the people. If it's an anonymous question, then we ask that maybe you reach out to us and we can help you with your situation.
Right. Okay, well, I want to thank everyone again. We'll see you in 2 weeks' time, hopefully, and appreciate the time that you spent with us today. Hopefully, you know, we entertained you and maybe gave you a few things to think about. So thanks very much.
And there's certainly a lot there that was covered in, a lot of generics. If you want anything specific on any kind of technology or interested in digging deeper in each one of those technologies, again, let us know.
For sure. Okay. Well, thanks, Paul. Thanks, Chris. Thanks for the help.
Thanks,
thank you. Have a great day, everyone.
Bye-bye.
Bye-bye.